Good morning, everybody. My name is Torsten Höfler from the Scalable Power Computing Lab at ETH Zurich. We are super happy to welcome Marian Verhelst this morning to tell us all about heterogeneous multi-core systems. She tells us it's an interesting talk that goes at a lower level that we are usually used to. But then I explained that we are doing a lot of low-level things as well. So we'll see. I mean, I'm super happy to have Marian. And without further ado, I'll give the word to Marcin, who's going to introduce her more formally.
Thank you, Torsten. Marian is a distinguished full professor at KULeuven and a research director at IMEC, specializing in embedded machine learning, power accelerators, and low-power edge processing. Among other things, Marian is a member of the board of directors of TinyML, IEEE SSCS Distinguished Lecturer, and was a member of the Young Academy of Belgium. Marian receives the Laureate Prize of the Royal Academy of Belgium in 2016, the 2021 Intel Outstanding Research Award, the Andre Mischke YAE Prize for Science and Policy in 2021, and 2 ERC grants. So without further ado, the stage is all yours, Marian.
Okay, thank you. Thanks a lot. And Torsten asked me to comment a bit on my relationship to IMEC. So I'm a full-time professor at the University KU Leuven, but I'm also part-time affiliated to IMEC, where I basically help them to set some strategic long-term roadmaps and to give advice on the topics that I have expertise in, which is then the machine learning architectures. So like say half a day, up to 1 day a week, I spend at IMEC basically. And I have some PhD students there as well. Voila. So that being said, let me dive into the topic of today. I want to talk to you about the research in my lab on heterogeneous multi-core systems. We actually built the chips on processor chip design, targeting EdgeML. So really doing machine learning in extreme edge devices. Phones are already on the high end for me. It goes even to more low power wearables, portables, can be robots, smart glasses, drones, whatever thing you can wear that has to work on a small battery, but has lots of sensors. And we want it to be smart, not by letting the thing send all its data to the cloud, which we don't want for both privacy, energy reasons, and latency reasons, but really by letting the device itself run machine learning algorithms to a first extent the inference part of it. Later we can add the learning. And then again, it was said in the beginning in the intro, is sometimes called TinyML, and there's an organization, tinyml.org, that's trying to bring together people that are active in that field, because it really needs optimization across the algorithms, the tools, the applications, and the hardware, and even the technology at the bottom, so across the whole stack, because you're so scarce in power and energy consumption. So people interested, it's a very rich community with webinars and meetups and lots of stuff going on. So it's highly recommended if you want to know more about that area to take a visit there. So question is, of course, why do I still do research in that area? You could say machine learning is already everywhere. Let me move this bar here. I hate the Zoom bar that doesn't disappear, but okay. Anyway, you could say it's already everywhere. In our phones, we have face recognition. On my phone also, I can talk to my phone. I have a car with smart lane assist and smart glasses. If you have enough money and you don't carry the bulky batteries, you can already buy them to a certain extent, use them for a variety of applications. But the problem is that's not really what we want. It's not that impressive yet, because yes, I have face recognition in my phone, but that's a really simple task that I can do with a rather small machine learning model. And yes, I can talk to my phone, but if my cloud connection is down, if I don't have an internet connection, I cannot really use a large vocabulary anymore, because the language model in my phone is very, very, very limited. And yes, I can have some lane assist in my car, but we don't have full self-driving yet. And part of that problem comes from the fact that I only can spend about 10 watts of power behind the glove compartment of my car, which is where I put typically these application processors. And with 10 watt of power budget, we cannot run all the neural or the machine learning models needed to enable full self-driving. And yes, smart glasses exist, but either they have a wire to a big battery pack, or they have this huge battery on top of your head. So also there, we're not there yet. So there is more work to be done to really make these embedded devices smart. And the question is, how far off are we? And for that, I will do some two back of the envelope calculations. Let's first start with the smart car. And let's very naively, and I'm stressing it's a huge underestimation, naively assume I need 6 cameras, HD, full HD, running at 30 frames per second. They could consume 10 watts, as I said, behind the glove compartment of the car. And that's then my naivety comes in here. I assume I just need a ResNet 50, which is a neural network, machine learning model in the form of a small neural network on every frame of my cameras to enable my self-driving. Obviously, I cannot do self-driving with the stupid ResNet 50 neural network. It's way too small. It cannot do any fancy things. But it's just to put an underestimation. If you take those numbers, you would need about 1 tera operation per frame. So 1 10 to the power or 10 to the power 12 operations per frame. And in total, hence 300 tera operations per second across my cameras and across my frames. And that I have to do in a 10 watt power budget, gives me an energy efficiency requirement of 30 tera operations per second per watt of power you invest. Is it a lot? Is it a little bit? We'll see later. Other side, smart glass. Of course, I don't need 6 cameras here. I'm happy with a stereo camera, but I cannot spend 10 watts. I only have a power budget of about 100 milliwatt. That's already quite a lot to survive on a battery for some time. And again, my naive underestimation that I can do very fancy things with a ResNet 50 on every frame. And then, of course, my throughput requirement is now less, only 30 tera operations per second, but I now have a much tougher energy efficiency spec, 300 tops per watt of power I invest. So are we there already today? That's the question. So I put here on the map, on the horizontal axis, my power consumption. This is 1 watt, 100 milliwatt, 10 watts. So these are my 2 cases from previous slide. And on the vertical axis, I have my throughput. Giga operations per second at 10 to the power 9 operations per second. So this is my 1 teraops, 10 teraops, 100 teraops. So these are our 2 targets. And let's now see where the state of the art is. First of all, CPUs and GPUs. I only put 1 CPU, efficiency of a CPU. And here, every green dot is a different GPU. And you see on one hand, you have a batch of GPUs that has a high enough throughput. They're the normal desktop GPUs. They're good, they're powerful, but they consume too much power, 100 watt-ish. There are low power GPUs, the one you see here, and there are even a few a bit more low power, but they don't meet the throughput requirements that we have. So with a GPU, we're not getting there. You could say, you know what, as a hardware designer, I think we can do it with FPGAs, because an FPGA allows me to do much more in parallel and customize my circuits. But if we look at the data, and every dot here again, or every triangle is an FPGA implementation of a machine learning model, a neural network typically, you see they don't really help. FPGAs are not at all efficient platforms to do any compute, because there's just too much overhead in the long routing connections and the inefficiency of the slices and so on and so on. So that's not the way to go. But people recently, over the last 10 years or more, have made a lot of specialized processors. Sometimes they're called TPU, tensor processing units, or NPU, neural processing units, or NNAs, neural network accelerators. And there are this variety of dots you see here. So those processors, they do get very high efficiencies, much better than these CPUs, GPUs, FPGAs here, getting close to, not exactly up to, but at least getting close to the workloads or the targets we put up front. So there are specialized processors developed both by academics, but also by Google, by Amazon, by Intel. A variety of partners are all making special processors towards neural network workloads. That's a machine learning model that's popping up the most these days. And the question is, how do they do that? Why are they more efficient than all these CPUs, GPUs? What is the magic trick here, basically? And some of these are also made by my lab. I'll talk a bit about these chips, mostly about the Diana chip that you see here in the middle. But all these dies are things we designed over the past few years. So what I want to do in this talk is, first of all, show you how we got here. Why is it that all these dots here are better than the CPU, GPU dots? And then the question is, okay, how to go further? What are the challenges? And my call will here be that we need more heterogeneity and or flexibility. And then I'll end with some future things we're working on right now, but we don't have the answer for yet. So how did we get here? To know that, I have to start by explaining where the energy goes in a machine learning processor. And machine learning, for now, I'm going to narrow it down to neural networks. I know that there is much more, and we're going to talk about more towards the end. Bayesian networks, probabilistic graphical models, all kind of other reasoning models. But for now, let's stick with neural networks. And I'm going to make it even simpler and assume that my neural network is every layer is just a matrix multiplication, a GeMM workload. And if I have a convolution, I will do an IM2 call or something to make it into this nice matrix multiplication, from which I will call the dimensions M, K, K, N, resulting in an M by N matrix. Or if you prefer pseudocodes, they're basically 3 nested for loops across my input channels here, my input, or my output rows and my output columns. And then the core of this, I just do a multiply accumulate. That's what I have to do, very efficient in an NPU processor. How does a processor then look like? Well, the least you need to have in your data path is a processing element that can obviously do multiply and accumulate. And of course, that processing element has to get the data from somewhere, which is a one or multi-level on-chip memory hierarchy with register files, local SRAM, global SRAM, you name it. And typically, even that memory is not big enough to store my whole input and weight and output matrices. So the data often still comes from off-chip DRAM or some other storage. And if you wonder where does the energy go in processing this kind of matrix multiplication workload, of course, we have to see what happens with the data. First, the data will have to be brought from off-chip into my on-chip energy, into my on-chip memory system, costs me energy. Then I have to bring it from my on-chip system into my data path in my local registers, close to my multiply accumulates, costs me energy. Then I do my multiply accumulate, costs me energy, but I'm happy to pay this energy. That's fine, I want to do this operation. And then I have to bring my result back, either to the SRAM on chip or to the DRAM off chip. If you want to make an energy efficient processor for my extreme edge devices, you have to realize that the sum of all these components is what matters in your total energy consumption. And if we don't optimize this processor at all, the pie chart here on the bottom will probably be more or less what you get. Most of my energy just goes to DRAM access, going off chip. Then I have a big portion going to on-chip data movements, and then I have a little bit of energy consumed in my PE, my processing element, to effectively do the computations. I would like the energy consumption to be the blue part and not that much the green and the yellow part, because they're just overhead of doing useful compute. So that's what people are working on. There are all these special processors that you saw, all these purple and yellow dots on my previous graph, they optimize for that. And they do that in 2 major ways. I mean, there's more tricks, but the 2 most important tricks are data reuse and reducing the precision of my compute. What does it mean? Data reuse basically is all motivated by our emerging Moore's law. And the graph you have on this slide is my favorite graph of computer architectures of all time, because you see all the trends. First of all, the yellow, we get more and more transistors, Moore's law. And in the past, people used it to make, first of all, processors faster and faster, the green dots, by going to deeper and deeper and deeper pipelines. But at a certain point in time, we all know, I started to have power density issues, and we had to stop scaling the frequency. Otherwise, the chips would melt down, and we just went to the same frequency from the 2005 age up to now, Luckily, we could still scale single-thread performance, regardless of not going into deeper pipelines or to higher frequencies. And the way we did this was by using the transistors we got to improve the performance of the processor by going more and more parallel. I started to have MMX instructions, SSE, AVX, AMX, more and more parallel data paths inside my processors. Secondly, when that starts to flatten off as well, we started to go, and as in the black part, to multi-core. I just start to put more cores because I get these transistors. I have to do something with it. And you see that that trend is also flattening down now. And the last trend you see come up, and it's not on the graph, is that we start to put domain-specific accelerators. I put multi-core, more and more cores. But now I don't put CPUs, extra CPUs, but I put GPUs and NPUs, TPUs, and so on and so on. So it's all using more transistors to become more parallel, both within my cores and across my cores. And why do I become more parallel? Well, in these neural networks, and especially in embedded devices, it is not to increase your throughput. I want to become more parallel to be more energy efficient. That's maybe a bit of a weird statement, I want to be more energy efficient because the parallelization allows me to have more data reuse. I get extra energy efficiency from parallelization because I can manage or deal with my data more efficiently. And to explain that, let's again look at the processor we have. It's very important to realize that in this workload here on top, every blue row will have to be multiplied with every red column here. That's what a matrix multiplication does. The first row multiplies with the first column, dot product gives me one output. The first row multiplies with the second column, dot product gives me the next output, and so on. But also every red column is multiplied with every blue row. So the data inherently, the workload has the capability of data reuse. In my data path, I can exploit that. If I don't have one parallel processing element, but many of them, I can give the same input data or weight data to multiple elements in a row. Or I could give the same input data, but I can share my data across more than one processing element. Beyond sharing input or weight data, what I can also do is not go to the memory for every partial sum of this dot product I compute, but doing the dot product and the accumulation already across multiple multiplications I have here. So don't accumulate locally, but accumulate the result of more than one processing element. That's also a form of reuse. I do output reuse in this case, basically. So I use my parallelization to enable my data to be reused. And the benefit of that data reuse is basically that I have to go to memory less often. The more I have elements on one row or one column or parallel data paths on which the input is reused, the less I have to go and fetch the same data from memory over and over again, both in my on-chip architecture as well as in my off-chip memory. And if you like to again see this in my nested for loops, it means that some of my for loops become for loops, parallel for loops that are executed within one clock cycle. And those, because they allow to share, or they share some data, these different loops, they allow to fetch all these data elements less because of the parallelization. The remaining for loops are still temporal, but also there in these temporal loops, we can exploit some data reuse. And the temporal data reuse happens through either, some people call it tiling, other people call it stationarity. But what we basically do is by ordering these temporal loops in a specific order, and by deciding which of these loops we allocate to which level of the memory, to local SRAM, global SRAM, off-chip DRAM, we can also be smart to not constantly have to go into DRAM for data fetching. But most data can be fetched from local SRAM, a bit less from global SRAM, and a bit less from DRAM. So also here, my extra transistors from Moore's law that allow me to put bigger memories on chip allow me to save energy both in my off-chip transfer and into some of the upper levels of my on-chip. So spatial data reuse and temporal data reuse are of crucial importance to get this energy efficiency from being completely memory dominated to being processing element dominated. And important to realize here is that it all boils down to juggling around these for loops and allocating them to the right memory level and deciding which of them I will parallelize in my data path and which of them I keep temporal. And that role, or that enabling that, has two responsible actors. On one hand, the hardware has to have the flexibility to be able to support different jugglings of this loop, to have different orders of my temporal loop and memory allocations, to have different parallelizations of my lowest for loops, because every workload has different dimensions. Some layers might have a very small, tall matrix, and other might have a very wide, but shallow matrix. All of them will require different unrollings to be efficient. The hardware needs to support that. But it's also the job of the scheduler. The scheduler is eventually the one that has to decide which loop juggle is the most efficient one that gives me the best energy efficiency. And we'll come back later in this talk that we built or try to build some tools that ease the job of the scheduler here. Okay, that was his first trick. Data reuse saves me lots of energy. After I've done data reuse, you see most of the energy hopefully goes to the processing elements themselves, if you have done a good job. And then the second trick that everyone uses is don't compute at 32-bit floating point. Obviously, if you do inference, but even if you do training, these processing elements can compute at much lower precision. For training, very often floating point 8 or sometimes floating point 16 are used. If you do inference, you go to 8-bit integer computation, or even 4 or 2 and sometimes 1-bit compute, where every weight, every input is only a few bits to communicate a few output bits. And of course, if we scale the precision of the processing element, it saves a lot there, super linear. You have some results here. For example, a floating point 16 multiply accumulate is already, let's say here, a factor 5 or so more efficient, less efficient than an integer 16-bit MAC. But if I then go to an 8-bit MAC, you see, we already have a factor 20 gain from the FP16 MAC. And if you go to a 4-bit MAC and so on, it becomes even better. So this is not just a pure linear scaling. It's super linear in the precision of my processor. But what's good news is that I'm not only scaling the energy of my PE, I'm also scaling still the energy of my on-chip memory transfers and my off-chip memory transfers, because they also benefit from this lower precision. I have to shuffle around less data bits. So most savings here, but also some savings there. So it's clear that everyone is doing this example, or every tensor core in a GPU can compute at FP16, but also int 8, int 4. And you can see here that the more you go to lower precision, the more parallelization I get. And that's because we typically split a multiplier into sub-multipliers. One 16-bit multiplier can become 2 8-bits or 4 4-bits. And hence I can compute more and more and more in parallel, the lower precision I get. And that's pretty cool, because it means that I can do more spatial unrolling the more I go to lower precisions. So again, it's a double benefit. I go to lower precision, less energy per operation, but more parallel compute, and hence even less energy for my memory transfers, because my data reuse improves again. So these are two very important aspects. Of course, it means that the algorithmic people are doing a lot of research in this community to figure out for every layer of the neural network, and you see it here for a ResNet 18, how many bits of activation does the layer really need, and how many bits of weights does the layer really need. And you see it's highly variable. They made the ResNet 18 work with perfect precision, with only 2 activation bits, sometimes 3 or 4, and with 1 weight bit, sometimes 2, 3, 4 for the different layers. Of course, and how they do this, basically doing differential search, where also how many bits you use for every layer is part of your learning algorithm. With the Gumbel softmax function, they see whether after some time, layer 2 needs the 2-bit path and layer 1 needs the 4-bit path, and so on and so on. But of course, it means from a hardware point of view, I have to support sometimes 2 bits, sometimes 4 bits, sometimes 1 bit. So all these combinations of precisions. Now, one recent trend that a lot of hardware people are very excited about, that seems to combine this trick 1 and trick 2, is in-memory computing. So I want to end by mentioning that, where what people try to do is maximize data reuse at a very low precision. And they do that by computing inside SRAM memories. And how do you do that? Again, we assume our same matrix multiplication. And the first thing you do is you load all your weights. And let's, for simplicity, assume a weight is a single bit weight. I load all these weights in my SRAM memory. So the first upper left weight goes into this memory cell, the next one in the next memory cell, all the way to the last one here. And then the next one goes here, and so on and so on. So every memory cell has one weight bit. And what I then do is I put my activations of one row of my activation memory, my input here, I put on the word lines of this memory. So the first element drives this word line, the last element drives that word line. Can either be with voltage modulation or amplitude modulation of my voltage, or with pulses, or you encode the data here on this line. What happens now in an SRAM cell is that it will provide current or charge to the bit line, the purple line here, depending on whether there is a 1 or a 0 stored in this memory cell, and depending on whether the word line is more or less activated. And this realizes a multiplication operation, because the current that will be injected on the purple line is now the effect of a multiplication of this weight bit and this blue word line value. And as a result, I inject an amount of current equal to this multiplication, but the next cell does so as well, and the next cell and the next cell. And what will happen is the total charge or current on the purple line will be representative for the dot product of this whole blue column and this whole blue row. And for example, on the last one, of this blue column and the last red row. So this basically does my dot product operation for many outputs, a whole row of outputs in parallel. People say I bring the compute to the data instead of the data to the compute. And that allows you to compute super efficiently, because I don't have to do these accumulations in the digital domain. They're in the analog domain, makes it very cheap. I don't have to move my weight data. I still have to move my input data. And I can have maximum data reuse, because this word line DAC can, for example, drive 512 different cells. So I have a spatial data reuse across 2 dimensions of 512 in one dimension, 512 in the other dimension. So my compute again becomes very dominant, and my data transfers, the pie chart of the data transfers shrinks, and then you get very nice energy efficiencies. Sounds almost too good to be true, and it is too good to be true. Because if you want to practically use that, you bump into a lot of challenges. And let's dive a bit deeper into that. First of all the dots you see on this graph are using all the tricks that I mentioned. They're trying to go to very low precision. I didn't brought the graph, but many of these dots are only 1 bit, 2 bit, maybe ternary compute. So they're very low precision. And many of the dots, definitely the yellow ones you see here, all the yellow dots are these in-memory compute blocks. So they do this trick of the analog compute in the memory domain. But if you do that trick, you get excellent energy efficiency indeed, thousands of tera operations per watt, for example, for this guy. But it is for the perfect, nice, ideal GEM workload. One where this weight matrix perfectly fits my array. It's nicely 512 by 512 in dimension, and everything fits wonderfully, and my peak workload has an amazing energy efficiency. But in a real neural network, not all my layers are like that. I might have a layer with depth-wise calculation, or I might have a layer with only 3 input channels, or with a very small filter, or one that's slightly too large, so I have to map it in 2 times. There's all kinds of reasons why this weight matrix doesn't perfectly fit, and this input matrix doesn't use all the rows. And if that happens, I'm underutilizing my data path. I may be only using 5% of all the compute cells, and everything else is overhead, generating energy and capacitance and so on and so on. And that's the problem with this graph. All the dots you see here, and here you have them for their precision, all the dots you see here compute at very low precision that not all neural networks tolerate. and mention or report their peak performance, the energy efficiency, if they're nicely, perfectly, fully used. This is not the workload performance. If I run a YOLONet on there or a ResNet or whatever, I'm not getting these numbers. I'm getting much worse because all these architectures get the efficiency by giving up on flexibility. This architecture is not flexible at all. If you want to use it for a different number of channels or a different dimension of the matrix, there is no hooks to adapt or multiplexers to shut down parts because it's highly optimized for this peak efficiency, giving away flexibility or utilization across workloads. And that we have to realize very well. Because what you see is the larger you make your array, so this is the dimension on the x-axis of this kind of compute structures. And they can be in memory or they can be digital compute arrays. Both have that problem. So the dimension of this array is what we're going to put on the x-axis. And on the y-axis, of course, the bigger I make my array, the more efficient my green line, my architecture becomes. And that's what the hardware guys like to do. Bigger arrays and bigger arrays and bigger arrays, because then I can have more and more and more data reuse. And then my efficiency goes up. And then you get things like the Tesla full self-driving chip that has a compute array of 96 by 96 digital multiply accumulates. Or you get these in-memory cores that have 500 by 500 computing SRAM cells. Very high array size, very high efficiency in the peak workload. But the problem is the algorithms, they have very diverse layers, big ones, small ones, and so on. And you see with this layer diversity, the utilization of my array, how much % of my compute units I'm effectively using when I do the compute of a real workload, it goes down with the size of the array. The bigger my array becomes, the more and more underutilization I have for realistic workloads. So it goes the other direction. And what you see, companies like NVIDIA and so on, they also have this data reuse in their tensor cores, but the tensor core has a much smaller dimension than these in-memory compute models or than the Tesla compute core. And that is because they have to guarantee for all their customers across all their workloads, they will still have a decent utilization. So here we're a bit stuck, and it's getting even worse towards the future, because then now we're just talking about the heterogeneity of neural networks, but we all know that more and more different algorithms are coming up to be combined with neural network, probabilistic graphical models, Bayesian models, MCMC models, sampling, and so on and so on. They're even more diverse than this. So what to do? We're stuck. From a hardware point of view, I want big arrays. From an algorithmic point of view, I'm not using these big arrays efficiently. And the only company that can do it are companies, for example, like Tesla, where you make the hardware and the algorithms in one stack with no external customers. I just make what I need, and then I can make very big arrays because I will adapt my algorithms to exploit them. And that brings us a bit to the hardware lottery problem that I briefly want to put on the map. The fact that the algorithms are very diverse, but the hardware wants to be efficient and is kind of stuck in some implementation paradigms. And it's a very nice discussion that Sarah Hooker started on that tension, basically, between these two fields. And she calls it the hardware lottery. She's a researcher from Google that says hardware platforms exist and they're very slow in their evolution because hardware takes more than 2 years to develop a new chip and so on and so on. Software algorithms like to change very fast. The software guys can develop things very fast. But the problem is the software that mobs best on the hardware is the one that wins. The software that best survives or has the best performance on the hardware of today, the GPUs of today, the CPUs of today. But the GPUs and CPUs of today, they're built many years ago because they take 2-3 more years to develop based on algorithms from many years ago, from mature algorithms at the time that these hardware platforms were conceived. So we are now selecting software algorithms based on hardware that's already old school. So how can we do real innovation? There is a deadlock because the software develops fast, but based on old school hardware that's developed based on software and algorithms from a long time ago. So this really kills our innovation. And what we should need is a way to enable the software to exploit more variety in the hardware, to have new algorithm paradigms come up and be used efficiently. And that's where my claim for heterogeneity come in, both to solve this problem, but especially in the short term, to find a way between this efficiency need from the hardware point of view, but this utilization struggle from the software point of view or algorithm point of view. And if you look at systems that we already have today, they are already heterogeneous, right? I have on a smartphone, CPUs, GPUs, NPUs. This is the Tesla chip I just talked about. It has NPUs, but also signal processors, GPUs, 12 CPUs, and so on. So these systems are heterogeneous, but it's not in this extreme edge domain, and it's not heterogeneous within this neural processor handling or neural workload handling. So that's what we went after, and what we really wanted was, on one hand, a chip that has the flexibility of a CPU to do all kind of pre-processing, autocorrelation, FFT calculation, the DSP functions that you might need, and manage the rest of the system. But that also has an AI core. Let me start with this one. On one hand, this kind of in-memory compute that can do extremely efficient, low precision compute at very high parallelism and data reuse, but also has the capabilities to do AI where there is not that high parallelism or where I need higher precision. And that's what we integrated in a single system. This was a chip that was designed in a 22 nanometer process, which integrates a CPU, RISC-V CPU, based on Luca Benini's PULP infrastructure, and then a digital AI core, and a digital regular AI core, and an analog AI core, which share data through a shared buffer, activation memory, but also have a larger shared global memory together with the CPU. And these cores are now optimized for very different things. On the one hand, the digital AI core is purely optimized for flexibility. Flexibility across precisions, flexibility across neural network layers, but it's a rather small core, so it gets good utilization across all these workloads. On the other hand, the analog core is purely optimized for throughput and efficiency. So 1,000 by 500, 500,000 multiply accumulates per clock cycle, but only if you can live with the low precision and if you have very wide data layers in your neural network. And the question now is, how do I now schedule workloads on there? Because my digital core, very flexible, but as you can see, almost 2 orders of efficiency less efficient than the analog core, computing at low precision. And some layers will prefer to work in the analog domain, some layers in the digital. Then the question is, first of all, how do they share data? What's the role of this shared level 1 memory between the 2 cores? And how do I then schedule each of these workloads on those 2 cores? Data sharing is very important in this. And to explain you, let's take a very simple example. I have this first digital layer, over the first layer of my neural network that I run on my digital core, and let's assume then 2 layers follow that run on the analog core. And in a naive way, I could first execute layer 1. When I'm done, analog core kicks in layer 2. And you can already see it's very inefficient. First of all, this analog core and digital core are idling a lot of the time. And the second problem will be that the amount of data that has to be transferred here from layer 1 into layer 2 to be computed in the analog core is pretty large. And this is a simple example again with the ResNet 18, where the first layers run on the digital core, the next on the analog. This is the latency we get if we map that on our chip and we measure. But this is the amount of memory that would have to be transferred from the digital core into the analog core. And what you see, it's about 1 megabyte. It's bigger than the size of this shared level 1 cache or memory. It's even bigger than the size of our level 2 on-chip memory. So it would have to go off-chip to DRAM to be able to do this compute. And that is terribly slow, costs energy. I don't want it. But what you can then, of course, do is realize that it's a convolutional workload in this case. I don't need the full green result to be able to start the red compute. I can break my green compute into different tiles. And as soon as one tile is done, that data can already be streamed to my analog core. So the analog core can start to compute layer 2 and 3, while the green core, the digital core, continues with the rest of layer 1, the second tile, the third tile, and so on. This is sometimes called layer fusion or layer streaming or streaming processing. And if you do that, of course, we're done faster because my cores are idling less. Nice. But I especially have a memory footprint benefit. I can now squeeze all the data that has to be transferred from digital to analog in this shared level 1 memory, and I never have to go to my global memory or even worse. Great opportunities, but the problem is that now I gave myself an enormous scheduling headache, an enormous scheduling problem, because now I no longer have to schedule layers on the cores, but small snippets of the layers. And that can quickly become a very difficult scheduling problem. The simplest one would have been if I just layer by layer schedule on a single core. Then I made my multi-core system where I could have to schedule my layers across my cores. But what I did now is I break every layer with this layer fusion. I break every layer into small parts that each have to be scheduled not only on a single core, but ideally across my multiple cores of my system. And that is the scheduling challenge I have now. And to do that efficiently, what we did is we built a complete analytical model of multi-core AI accelerator systems that try to predict for a given neural network workload and a given hardware architecture that you can define, multi-core, single core, with a lot of memory hierarchy or a shallow memory hierarchy and so on. How much energy latency does it cost me to run that workload on that core for a given schedule, for a given mapping or execution schedule? And you have many possible mappings. Every neural network can be mapped on any core in many different ways, giving a different energy latency trade-off. And you can pick either the lowest energy solution or the lowest latency solution and so on. And it boils down, of course, to the cost function you then put. So for example, you can say, give me the lowest latency solution. And this is a small example of the tool. By the way, it's available in open source. You can just go to our Git. But this is a small example of the tool. We map a very simple 4-layer neural network that we break into 6 pieces for each of the layers. We schedule it across 3 cores with a common communication bus and DRAM port. And we ask for the most latency efficient schedule. And here you see the data dependency between the different layers through all the lines. And then the system also, or the tool also tells me how much memory does every core needs to fulfill this schedule. And suppose your memory consumption is too high, I don't have that much local memory. You can also tell the system, give me a memory optimized schedule. And you will see that he starts to spread out the workload a bit more, but now it fits a smaller memory footprint because my data that's produced is consumed much faster. So we also applied this to the Diana system. So this is the hardware representation of this Diana chip that we made. We map again this ResNet on there. And you see that, for example, he assigns layer 0 to the digital core because it only has few input channels. So it doesn't map well in the analog domain. Everything else can very efficiently run on the analog domain. And you see he schedules it. He sees what are the memory footprints throughout time of this mapping of that network on those cores, what's the latency, what's the memory usage, and so on and so on. Of course, and I'm starting to finish down this talk because I see I'm running out of time. But of course, once you have that, you don't have to just put in the Diana system. You could use this to just play around with architectures. And that's a bit what we're doing at the moment to, for example, try to answer questions like, is it better to have one very large core, AI accelerator core, an NPU or TPU with a lot of memory? Or is it better to have multiple cores with smaller memories? Because this will give me better utilization, but less efficiency. What is the trade-off here? Or should I make multiple cores, but make them heterogeneous, as I said, as some in-memory compute, some maybe more digital, some with different data reuse, data unrollings, and so on. So without going into all the details of that, we're writing a paper on that now. But it starts to show that heterogeneity makes sense, but not for all workloads. It really depends, of course, on how heterogeneous the workloads that you're interested in are. This brings me a bit to, I talked to you about what we did. What are we doing at the moment is what I want to end up with, or what I want to end with. And if we look forward, clearly we see an increase in the variety of the workloads, and neural networks become more and more diverse themselves. But on top of it, we see that even beyond neural networks, people start to combine the neural nets with reasoning models on top, either reasoning logic formulas, or we're doing graphical models on top of Bayesian networks, of neural networks. It's a variety of algorithms that will have to be combined together with low-level pattern recognition with neural nets and then reasoning layers on top of that. And the question is whether we will need even more accelerators then, because the workloads get more diverse, even more heterogeneity. And the problem is we cannot. And the reason we cannot is because we start to do something very weird with our carbon footprint. And this is data from, something I got from Carol Jane Wu at Meta that does a lot of research at that. On the left, you see the carbon footprint of an old iPhone. The black part is the operational carbon footprint, the energy consumption during the lifetime of the device. The gray part is the embodied carbon footprint, the carbon footprint from manufacturing this system. And then we look at the more recent, it's not that recent anymore, but a more recent phone. And what you see, the black goes down. Yes, clearly, because we make more energy efficient systems, more data reuse, smaller transistors, all the hardware tricks to consume less energy, survive longer on a battery. But you see at what expense we did it. The manufacturing, the embodied carbon footprint rises because we add more accelerators to the same chip. We go to more advanced technologies for all of this. It is costing us more than it brings us across the lifetime of the phone. So we cannot go to more accelerators due to the carbon footprint. On top of that, we're still stuck with this hardware lottery where algorithms take very fast to develop, but they do it on this old school hardware that doesn't go very fast in the development cycle. We need to find ways in a carbon fair way, let's say, to allow the hardware to develop very quickly together with the software, and this across many workloads. And that's what I'm working on with my new ERC project, where we will try to make very modular, okay, let me explain it here, very modular cores in which different accelerators can easily be plugged in. We call it Snatch. It's based on the Snitch interface from Luca Benini again, but we modified it to easily support accelerators with many ports into a local memory. And these accelerator shells, you can see it as an accelerator template, are designed such that they can very nicely be mixed and matched together in a common system with a common NOC or Axibus, depending on how many of them you need. And the idea is then to build a library of these kind of snacks accelerators for different workloads and build the tools to quickly assess, to quickly assess which accelerator combination do I need for a specific algorithm at hand here, for example. To very easily mix and match the right accelerators together. Of course, it also means we need a compiler for this mixed accelerator combination, which we're also trying to develop through MLIR. And of course, once you have that, is the question, do you then tape out that chip for that specific algorithm? But then again, it takes me 18 months. That's not the right way to go. If we really want to have this fast-paced hardware development in tandem with the algorithm development, our idea is to build some pre-made chiplet libraries where every chiplet has one of these accelerator or one or a few of these snacks accelerators on there, but they're made in such a way that on a reusable interposer, they can be put together in many different constellations, depending on one hand on my need of my application, how much power can I spend, and on my need of my algorithm, what is it in terms of combination of processors that optimally suits the algorithm that I'm interested in. As I said, that's a bit what we're going after now. I don't have this yet. I hope in a few years I can give a talk where we show some of these results. And with that, I end the talk. I think heterogeneity is important. It can bring a lot of gains to when you specialize, but we have to be able to do it in a very modular way. We will need to have custom compilers that can very easily deal with this variety of accelerators because we have to very quickly be able to cycle these different platforms. And that's what interests me a lot. Voila.
Thank you. Thank you a lot for an amazing talk. I will take the moment right now to make an advertisement for the MICAS happening in 2 weeks on the 9th of November. We will have Victor Prasanna from USC, and he's going to talk about scalable graph machine learning. Now, are there any questions in the audience? To have a question, you're free to put it either in the chat or raise your hand, and I'll unmute you. I can already see that Patrick is there, so you should be able to unmute yourself now, Patrick.
So thanks a lot for the very interesting talk. I have a question about the precision of processing in memory in the analog domain.
Yes.
You mentioned that when you build a chip, you would decide for one certain precision for the processing in memory. But what I was asking myself is, can you somehow steer this precision when you build the chip, or is this based on the physics of the SRAM?
That's a very good question. It's a combination of the two. So first of all, normally people indeed just build it for one precision. Can either be ternary as a 1.5-bit weights. People have proven 4-bit still works nicely. If you try to do 8-bit, you typically run into really physical problems. And the reason is that the noise on this purple line is basically is one of your biggest enemies. And the noise on this line comes from becomes worse if you hook up more of these devices to that line. And also if you have very long lines, on one hand, I want a long line because then I have a large dimension, good for my efficiency. On the other hand, if you have a long line, you start to have resistive drops on this line. And that again gives saturation effects and all kind of imperfections that will impact the accuracy of this system. And you can again try to optimize it, but then it becomes less energy efficient. So typically, you choose at design time, do I want a 2-bit system or a 4-bit system, or if you're very brave, 8-bit, but most people don't get efficiency there anymore, and that you then implement. There is a bit of runtime flexibility you could think of where you activate more columns if you want a high precision compute and less columns if you want, for example, with 4 bits, you activate more columns, and with 2 bits, you shut some down. But even then, your noise spec for the 4 bits will be the one that determines how you implement this. So that's the energy cost and the energy efficiency price you will pay. Does that answer your question?
I think I have to ask Patrick to unmute again, because otherwise he cannot unmute himself.
That answers my question. Thanks a lot for the explanation.
Okay.
I think the second person was Torsten.
Okay, yeah, thanks. I'll make it short. I have a ton of questions. There's one thing that is interesting. So you mentioned the hardware lottery. Well, there are many things that are interesting, but one that I want to emphasize here. You mentioned the hardware lottery. Actually, I have a comment first, because I don't think it's a lottery. It's a gravity well, because the hardware is not random, and the algorithms that result are not random. You have an architecture, and then everybody optimizes for that architecture. There's basically zero randomness involved. It's I would call this a gravity well.
Oh, I think the randomness is the architecture. I should take the other slide.
But no, I'm sorry. Have you worked with computer architectures? They're not building random chips. They're very carefully designing the architecture for the workload that they anticipate.
Exactly. Yeah, but they're designing it for the workload of the past. Okay, maybe, yeah, maybe.
But there's no randomness. This is the work. Exactly. This is the problem. Like it's a gravity well. Like we have the past, and it pulls us towards the past. There is no random element in the whole thing. But now this is a problem. I agree. So this is a huge problem. But what's now happening is interesting. If you look at the development from Volta, Turing, Volta, and Ampere, and now Hopper. You mentioned you mentioned int4. Mm-hmm. They got rid of int4 in Hopper. Do you have any? This is somehow diametrically against what you mentioned, like small data types, small things. And NVIDIA, the company that causes that gravity well, now says, "Oh, int4 is out of Hopper." So I was shocked personally. But do you have a?
I wasn't even aware that int4 was out of Hopper, but because I saw some of their platforms, they start to add int2, right?
Well, maybe that's on the inference side. Then we need to look more carefully. But the H100, we should check. It's gone.
I will check. If you mention the H100, I think there is another reason. do you know why they built the H100 instead of the H800? So the H800 and the A800 were their massive, excellent training platforms. But they both violated the China ban from Biden. So they started to develop a chip that would still be okay under the strong regulations of the US for export control. So they built the H100 and the A100 because they could still sell them to China.
I think it's slightly different numbers, but yeah.
Okay.
And that was ended last week, by the way.
Yeah, it was ended last week, but maybe it has to do with that. But okay, I'll look it up. I don't know about the Int4.
Yeah, that would be something to follow up on, yes.
I think for training, Int4 is not that useful, but for inference, it doesn't make sense. So maybe it's NVIDIA realizing that they're a very good training machine, but that they care less about inference. I don't know.
Yeah, I was shocked. Oh, okay, thank you. I have more questions, but I'll let Greg speak.
I guess to add on upon this randomness, I think the one randomness that I could see is that, you know, even if you have a very good algorithm, it doesn't necessarily need to survive the time, right? Depending on how you advertise it and do things like that.
What do you mean with the timing?
In terms of like, because you have this hardware, like you have a hardware, right? And you have a lot of software algorithms developed specifically for this hardware.
Yeah.
But the randomness, I think, comes from the lottery here, comes from the fact that you have a bunch of them and not necessarily the best is going to survive, right? So it's just a population, and depending on the situation and your, for example,
true. What I guess what Torsten says is the best will not survive, but it's not a random act. It is indeed a gravity well, because one is just closer to the architectures of today than something else.
There's still no randomness.
Yeah,
right?
but yeah,
you pick the one that is closest to what works and that has been designed in a process that is closest to what worked in the past.
Yeah. It's a more philosophical debate, but I agree. Yeah.
Greg?
Yes, thank you very much for the excellent talk. I really enjoyed that. So I have a question about this. So you presented this big spectrum of devices from like data center GPUs to this embedded small devices, and for example, these trade-offs between, let's say, what decisions you make for the hardware. But actually, I'm interested in you started with this edge devices, and I wonder if there is actually a threshold for algorithm design that, for example, you have a fundamentally different concept for designing algorithms, for example, for this data center GPUs versus these very small embedded devices. Because how I see it, how you presented it, is basically, also you mentioned that, for example, this spatial reuse, aka tiling, or in compute memory, etc., etc. So all these algorithm tricks or designs are all across the domain. So is it that whatever you are on this very one spectrum of the field versus the other, from the algorithmic point of view, they apply to the whole domain, or there are some algorithms that are reserved for one side of the spectrum or the other?
That is a very good question. I don't think there is humongous differences in paradigms used in the cloud and in the extreme edge. I think in general, the extreme edge is willing to give away a bit more accuracy in return for efficiency, just out of a need. You cannot fit in more memory and not have more energy than a certain limit in these edge devices. While in the cloud, you still see a strong trend to more accurate models and more, even if they become bigger and humongous models. So I think that's maybe one different shift. And for that reason, the models in the edge are a bit less diverse and crazy than some of the models in the cloud, where every single trick of the book is pulled to push the accuracy yet a little bit higher. I think a second, maybe small or a second difference is that in the cloud, I care only about throughput. I mean, in terms of timing, throughput matters. In the edge, also latency matters. And the result is that typically in the cloud, I can do batch processing for my inference. I can do batched inference. And in the edge, I typically have to do single image or single element inference. And that has some consequences on the parallelization dimensions you can exploit. Parallelizing across the batch, I don't do it in the edge. I do a lot in the cloud. But they're not massive differences. They're just subtle differences.
Okay, thanks. I also have more questions, but let's do round robin, I guess.
Okay. Any other questions? Ben, let me unmute you.
Hello. Yeah, I really enjoyed this talk. I'd be a bit interested in this scheduling, because I think you mentioned that you built this cost model, and I was wondering how much this cost model is heuristic and how much it is 100% accurate.
That's a very good question. The cost model is a pure analytical model, and how accurate it is depends on how much we tune it to an architecture. So if you use it out of the box and I just dream up the generic architecture and I code it in, then it allows me to relatively compare to other architectures with some changes, more memory, less memory, and so on. Of course, if I then tape out my chip and I look at, is it actually exactly the same? Then it depends on a lot of things, like exactly what protocol do I use on my bus? Exactly, can I overlap my memory access with my compute or not? And so there are quite some hardware details that matter if you want to get, we never get cycle accurate, but if you want to get into 5-10%, or even a bit better than 5 to 3% accuracy. So we can, so for our chips, we can make it to match fairly well, but we then still have to add some extra analytical nuances, let's say, into our formulas. For example, in Diana, just to make it very concrete, in Diana, the way you go to the level 2 memory, it needs some setup time. So if you access a batch of data or a single element or a couple elements at completely different memory locations, this has a different latency. This is in this way, in this system, if I build a second chip, it might have another communication protocol. If you ignore all these details, then of course you never get the perfect matching. At the other hand, if I'm doing studies or comparisons like this one, should I have this system or this, I care less about the exact communication protocol I use, unless it would fundamentally change my opinion. But you see typically there, the differences in performance are like order of magnitude. So then these fine nuances don't count that much. If we try to do something like here, I schedule on my exact chip, then we first tune our model to better match, and then that works. Yeah.
Very interesting. Thanks a lot. So for me, yeah, I'm more of a software person. I'm always fascinated by how in hardware there's more control over clock cycles and such things. Because in software, I never know when my thread gets scheduled, what my operating system does, etc., etc. But I feel like you also are going to hit limits when you have like dynamic workloads or things that are unpredictable, right? Definitely.
And I have to indeed stress that at this moment, it's of course relatively easy for us because this is a completely, let's say, compile time scheduled system where, yes, I have a CPU, but it doesn't have a very fancy operating system with a lot of dynamic decisions. It's rather bare metal, and it instructs the cores to do certain things, and it knows who needs the bus when and so on, and then you can do this. I agree with you. As soon as I start to put an actual operating system on here that also has other tasks and might get interrupted while doing things, and that as a result, the digital core might do something while the analog core also wanted to do something because they're not fully synchronized, and hence I have a bottleneck or a stall on the bus, and everything gets less and less deterministic. Then it's much harder to predict. And I think I have two answers to that, or starts of an answer. First of all, we're working here mostly focusing on embedded devices where latency is so important, and typically they only have very lightweight. I'm not talking about phones, but really about some more bare metal embedded devices, they have only very lightweight controllers and operating systems and so on. Secondly, I do agree that going forward, we have to look at more dynamism. So what we're doing now is in this model, we're starting to make it a probabilistic model in the sense that every hardware component has a certain performance, latency, energy, and so on, but it's not a single number in function of its parameters. It is a distribution function. So basically the bus has a certain bandwidth. I go here, the bus has a certain bandwidth, but it's not a fixed bandwidth. It's a probability distribution. Depending on what the CPU is doing, it might have a bit more or a bit less bandwidth available to one of the cores, and so on. And if you make these probabilistic parameters in your model, and we're trying to find a way to then do the probabilistic analysis of that, at the end, you get an energy distribution and a latency distribution that you can expect. And you can try then to design that the average is still fast enough, or the 3 sigma case is fast enough, and so on. But that's something we don't have today, but we're building at the moment. I don't know whether you think it would solve some of these problems you raise, or you have other thoughts in that regard.
No, I think sounds like a good idea. I'm not too much into this area, but it sounds really amazing. Thanks a lot.
Okay.
Greg, do you still have a question, or just raising a hand?
Yes, I do have a second question. So about this hardware spectrum design. So where you compared, for example, this Tesla huge chip versus NVIDIA, and let's say flexibility versus performance. So
yeah,
actually, well, why not go full Tesla in the sense that why not actually focus on really this very, let's say, maybe not flexible, but very efficient hardware, and maybe actually instead of focusing on this flexible hardware design, just let's say have really go in this direction of companies designing the whole stack from hardware to software, and then basically, okay, I understand that they will not be flexible, but maybe we can just spawn enough dedicated hardware that it will pay off because of this huge efficiency benefit.
Yeah, but what you're doing then is move more into, let's not call it a lottery, but into this gravity hole, right? You design a very, very dedicated, customized piece of hardware where all your algorithms can adhere to, but you go away from the diversity in the hardware, but definitely in the algorithms. And maybe there is another more efficient model that had a different hardware dimension and algorithm combinations, but we will never know because that can never be explored anymore, right?
True, but I'm just this thing. So if somebody takes an opportunity to at the same time design new hardware and algorithms, so if you're not only the hardware company, but for example like Tesla, you know what you will need in the future for the algorithm side, and you are designing this hardware for your needs in the future, and not for now.
If I know now what algorithms I need 3 years from now, I can do that. But the question is whether that's realistic. Can I predict now in 3 years what neural nets or other nets will be the most efficient or the most interesting ones? It's very hard, right? Think 3 years back, we hardly had heard of transformers and all these encoder-decoder architectures. This chip can probably not support them well because it's not that efficient to do these matrix mul workloads. How could they have known at that time? But it takes more than 2 years to design a chip, tape it out, go through all the verification, the validation steps, and actually deploy it. By the time you have deployed it, there is a very high chance it's outdated for the algorithms we have by then. So it's a big gamble. Maybe that's more a lottery than the original lottery I talked about.
Well, the unfortunate fact in exactly that game, and I'm involved in these designs in some companies, is that nobody is brave enough to make the step away from the gravity well, right? Because if you're investing, let's say $200 million in taping out a 3 nanometer chip, are you going to take a big risk? Will anybody design an algorithm for your chip So you won't take a risk unless it's more than a 10x benefit that you're seeing. And it's very hard to see a 10x benefit in that area that's so highly optimized as you describe. So
that's my gamble or my lottery with these chiplets. One of the goals or one of the ideas is we are de-risking. I'm not making 100 square millimeter new SoC with another fancy combination of all these different processors. No, I'm just making 1 or 2 new tiles in my deck, and I combine them in a different fashion. And that's then I don't need a 200 million investment. I maybe need a few million to develop 1 new tile and a few million or less than $1 million to put them together and try it out. And tomorrow I can put them together in a different fashion.
Exactly.
So that's a bit the idea.
But today chip designers are not there yet. But this will come, absolutely.
I think the problem today is, the biggest problem is the energy consumption to go from one chip to another is orders of magnitude worse than on a single chip. So it's on one hand still an energy and bandwidth issue. The other problem is we don't have the compile infrastructure today to very efficiently support this, but also this and also this, all these different combinations of different accelerators in one deck, and how to easily determine what to send where and generate the code and so on. But there I expect a lot from MLIR and more flexible backends in the compile stacks, but we'll see.
Great, thank you.
Actually, I would like to add, I think there's also a lot of innovation lost that's on the software side, because I think on the software side, we're also stuck in this hardware gravity, or like in this gravity well. So I worked a bit with climate and weather people as a performance engineer, and we just kept preaching to them, write code that works well on GPUs or that performs well on GPUs. And we kept preaching to them over and over and over again. And I think it's a huge shame because we're designing these algorithms for the hardware that's available. I think it could even go further if you think about neural networks. Why are they the dominant kind of model in machine learning? I think they work pretty well on GPUs, right?
Yeah, definitely. Yeah, and that's exactly what we're trying to do, because there's so many interesting, like some product networks and all kind of probabilistic graphical models, which we made some processor for that. They're not very popular now because they are terrible on a GPU, they're terrible on a CPU, they're terrible on an NPU. We easily get a factor 50 more efficient execution by making our own chip. So that's a chip we published 2 years ago or so. But no one uses it because, you in a full SoC, it doesn't make sense maybe to have it in all the SoCs. But again, maybe in this scheme, that kind of things can give their gradual market appearance. You first try it as a kind of add-on to an existing system, and it's interesting, I use it more and more and more. So it's a lower threshold to launch new algorithms into the pipeline, let's say.
Okay, I don't see any other questions.
Okay, well, it was a fun discussion. Thank you.
Yeah, thank you. It was great. Yes.
Thank you a lot for the amazing talk, and hope to see you all in 2 weeks.
Bye-bye.
Thanks, Marian.